All right. So we are going to go ahead and talk about topic 7.1 and 7.2 today. These shouldn't be too bad to kind of pick up through this video. But if you have questions, please let me know. We'll have a Google Meet at 1 o'clock on Monday. So if you have questions, you can come then. Hopefully it's before 1 o'clock on Monday that you're actually watching this video. All right, so this next unit is all about differential equations. And the whole unit is basically talking about equations and solving equations that have differentials in them, and differentials are derivatives. So really a differential equation is an equation that involves x, involves y, and it can involve the derivatives of either x or y, or second derivatives or third derivatives. So a differential equation has our variables x, y, but it also has derivatives as a part of it. So we call them differential equations. So, for example, a differential equation might look like, I don't know, something like this. Maybe you have x plus the derivative of y is equal to 2y. It is a differential equation. It has both x and y like we used to in a normal equation, but then it also has a derivative. It could be something like, hey, the second derivative of y plus the first derivative of y is equal to 0. That's a possibility because it has the derivatives. It does not have to contain both x and y, but it just has to have its derivatives in there. You could also see something maybe like f prime, right? Because f prime is technically the derivative. So f prime of x, maybe times x, regular x would be equal to the, I don't know, the second derivative. Those are all differential equations, and they can be in any form: plus, minus, times, divide, square roots, all that fun stuff. Exponentials, we'll actually see quite a few exponentials this unit. And so those are just kind of some examples of differential equations. All right, so a solution to a differential equation is a function that satisfies the equation itself. So for example, if I had a function y, and I'm talking about this middle one here, and I took its first derivative and its second derivative, and if I added those two things together and got equal to 0, then it would be a solution to this differential equation. So typically when we say solutions, we're saying x values, right? Like what does x equal? But for differential equations, it's a function that is a possible solution. And it's possible to have a what we call singular solution, where you have just like one specific function, or you could have a set of functions that work, and that's called a general solution. So you'd have more than one function that would be a possibility. All right, so in this first section, 7.1, we're going to talk about just writing differential equations. Hopefully this first part doesn't go too bad. And then in 7.2, we'll talk about verifying that functions are solutions to differential equations. All right, so here is your first example. A particle moves along a straight line. Its velocity v is inversely proportional to the square of the distance s has traveled. Which equation describes this relationship? And so looking at these multiple choice answers, inversely proportional means that there's some kind of constant, some kind of k, and that inversely means that your variable is in the denominator there. You're going to, whatever it's inversely proportional to, it goes in the denominator. If it's directly proportional, it would be with the k in the numerator, and there wouldn't necessarily be anything in the denominator. So that's why you see these fractions here, and that's why all the fractions have the k on the top. So far, everything is representing inversely proportional. It's inversely proportional to the square of the distance. So anything that doesn't have an s squared at the bottom is not our right answer. It's not inversely proportional to time squared. It's inversely proportional to distance. In this case, is s squared. And so now we have to break down, is it v of t equals or dv dt? And so it says the particle moves along the straight line. Its velocity is inversely proportional. Well, velocity, v, could be thought about as the derivative of s, right? And so this is the derivative of v. So this one is technically talking about acceleration. So that is not the right answer. Well, the derivative of s is v, and that one just has the v. So yes, this is not technically written as a derivative, but know that v of t would be ds dt, right? Because of our relationships. It just was written as velocity instead. So B is the correct answer there. All right. If you have some questions about direct and indirect variation or inverse variation, read through this box. You can just hit pause. I'm not going to go through it. It's not super crazy, but just kind of like, hey, recap of what was talked about before. All right. So example 2, a puppy gains weight, W, at a rate approximately inversely proportional to its age, T, in months. Write an equation that describes this relationship. So puppy gains weight at a rate. So we need the rate of the weight, which is the derivative. So dW dt is going to be equal to inversely proportional. So that's going to be a fraction with a k on the top to its age t. So t goes in the denominator. Write an equation that describes this relationship. Well, here it is. That's a cute puppy, by the way. All right, the learning rate for a skill is proportional to the difference between the maximum potential for learning that skill, M, and the amount of skill already learned, L. Write an equation that describes this relationship. So the learning rate for a skill, and it doesn't tell us the overall learning rate, it tells us the potential for learning the skill is M, and the amount of the skill that's already been learned is L. So we need a variable to describe like the overall learning rate. So I'm just going to call it S, if that's okay with you. And so the learning rate for a skill, so it would be ds dt, is proportional, and this is directly. If it doesn't say inversely, it's talking about directly proportional. So there'll be a k here. To the difference, difference means to subtract. So the difference between M and L. So M minus L all gets multiplied by K. So here's an equation that describes this relationship. All right, an IV administers medication to a patient's bloodstream at a rate of 3 cubic centimeters per hour. At the same time, the patient's organs remove the medication from the patient's bloodstream at a rate proportional to the current volume V of medication in the bloodstream. Which equation describes this relationship? So looking at these, they're all set up at dV dt. And then it is administered at 3 cubic centimeters per hour. So they're all going to have a 3 in them. That's why you see 3s in all of them. And then it says at the same time, the organs are removing the medication at a rate proportional. So that's a proportional rate. So that's a K, right? To the current volume. So that would be KV. And so if you think about it, there's going to be 3 cubic centimeters per hour. And then what's going to happen? Well, this is removing, so there should be a subtraction sign between those. So we're going to go with A for the correct differential equation there. All right, and last but not least in this section, a chemical is diluted out of a tank by pumping pure water into the tank and pumping the existing solution out of it. So the volume at any time, T, is equal to 20 plus 2T. So this right here, they said, is the volume. The amount Z of a chemical in a tank decreases at a rate proportional. So rate proportional means you're going to have a K on the top, right? 2Z, so KZ. And inversely proportional. So inversely means that this next piece goes in the denominator. Inversely proportional to the volume. So V goes on the bottom. What equation describes this relationship? So taking a look at what we kind of have going on here, it definitely B is out, right? There's a KZ minus something, and this one's out too. I don't even know what's going on there. And so you kind of have some options here. Definitely this one looks like it might be the reverse of this one, right? They're the exact same, just flipped around. And so if you remember, we said V was equal to 20 over 2T. So this V on the bottom, we can say is 20 plus 2T. So that means that I'm actually looking at this one here. The negative is because of the word decreases. And then the amount of chemical Z, that's why we have dZ dt at the beginning. All right, the nice thing about the rest of this unit is they don't really ask you to write the differential equations that often. So if you struggle with some of these maybe slightly more complicated ones, it's okay. We're going to kind of have some basic differential equations that we'll use moving forward. And so as long as you know how those ones work, you'll be fine. So this first one kind of just like an intro to differential equations, but definitely isn't like super heavy on the AP exam itself. Like if you see one, you might see like one multiple choice question that has to do with something along those lines. But for the most part, there's kind of some standard differential equations that we'll have, and we'll talk about those in a lot more detail later on in this unit. All right, so last section we're going to cover today is topic 7.2, verifying solutions for differential equations. And so we are going to check to see if the function that they give us is a solution or not. So for example, we have determined whether the given function is a solution of the differential equation f double prime minus f equals 0. So we want to know, does sine of x, is that going to make this equation true? So sine of x would just be this piece right here, right? In order to get the piece in the front, f double prime, you actually have to find f double prime. So the derivative of sine is cosine. And then the second derivative, so the derivative of cosine is negative sine. And now you're going to plug both pieces into the equation to see if it makes it true. So plugging in f double prime, it would say negative sine of x. And then we have minus sine of x. That's our original f of x. Does that equal 0? And it's super close, right? If it was plus and minus, then the answer would be yes, but technically it does not. So no, this is not a solution because it does not make that equation true. All right, the next one, 4e to the negative x. So your first derivative, because we're going to check the same equation, would be 4e to the negative x times by the derivative of the exponent. It's the chain rule, right? So times by negative 1. So I'm actually just going to make that 4 a negative. And then f double prime would be negative 4e to the negative x times by the derivative of the exponent. So times by negative 1 would make that a positive. And so we're just going to plug it in and see if it is a solution. So we have 4e to the negative x, our second derivative, minus our original function, 4e to the negative x, and does that equal 0? And the answer here is yes. So this function is a solution to that differential equation. All right, last one for this specific equation. If you notice there's a c in the front, that's just a constant, essentially. It's being multiplied instead of being added, and that's okay. So we're just going to work with the c, essentially, as just being a constant, a c. So a first derivative here, well, the derivative of e to the x is just e to the x, and so that would just be c e to the x. The second derivative is the derivative of that, which, once again, is c e to the x. And so then if you plug this in, you'd have c e to the x, the second derivative, minus the original function. Is that equal to 0? And in this case, the answer is yes, because the c is the same value throughout. All right, this is what we call a general solution because it does not matter what number you pick for c. C could be 50, c could be pi, c could be -8. Whatever number you pick for c, it will make the equation true. So this is a particular solution. There's one function, this function doesn't change, right? And that is a solution. And then this is what we call a general solution. There's lots of functions that meet this form where there's lots of constants that could go in the front there. And whatever constants in the front there, it's going to work no matter what. So we kind of did it in general. Does it work for all of these types? And since the answer is yes, that is what we call a general solution. All right, so determine whether each function is a solution to this differential equation. The derivative is equal to 4y over x. So we have y. We have to find its derivative. So we're looking for dy dx. Well, the derivative of 4x is just 4. And so now you're going to plug each piece into the equation and determine if this is true. So dy dx is 4. Does that equal 4y? And instead of putting in a y, I'm going to put in 4x because y is equal to 4x over x. And so take a look at what's going to happen here. You're going to have 4 times 4, which is 16. So you'll have 16x over x. And so on this side, you'll just have 16. So this is saying, is 4 equal to 16? And it does not equal. So no, this is not a solution. All right, next one, dy dx would be the derivative here. So 4x cubed. And then we're going to check to see if this is a solution. So 4x cubed, does that equal 4y? Y is x to the 4th over x. And it's pretty easy to see that, hey, x to the 4th divided by x would be x cubed, and 4x cubed, 4x cubed. So the answer is yes, those two are equal. So y equaling 4x or 4 to the power of x is a solution to this differential equation. All right, and last but not least, we have this lovely fraction. Remember, this is x to the negative 5th. That'll help you when you go to take this derivative, right? So dy dx, bring the power down, and then subtract from the power, right? Negative 6. And so we need to know, is this a solution to this differential equation? So we have negative 5, x to the negative 6th will equal 4 times y, which is x to the negative 5th, all over x. And without getting into the variables on this one, I think it's pretty obvious that the answer is no, because this has a negative 5 in front and this has a 4 in front. And so even if the variables do end up being the same powers, you're not going to have the same coefficients. So right away, you can kind of see, hey, the answer is no. By the way, they do actually have, this is x to the negative 6 and this is x to the negative 6. So the powers were equal. It was the coefficients that were not. All right, and last example for today, it says, for what values of k, if any, so that means that there might not be k's, and that's why they give us answer choice D, is y equals e to the 2x plus k e to the negative 3x a solution to this differential equation? So we need to know what value of k makes it a solution, or if there is no value of k that makes it a solution. So our y is e to the 2x plus k e to the negative 3x. And to figure out if it's a solution, I need y and I need y double prime. And so I'm going to have to find the derivative and then do it again. So the derivative of e to the 2x is 2 e to the 2x. So remember, e to the 2x is e to the 2x and then times by the derivative of the power, the chain rule essentially. And then here, this would be, you'd have e to the negative 3x. And technically, you'd have k e to the negative 3x, right? And then times by the derivative of your exponent there, so times it by negative 3. So negative 3 k e to the negative 3x. All right, second derivative. So this would be e to the 2x and then times by 2, so that'll be a 4 e to the 2x. And then here, this is not a chain rule or a product, or sorry, it's not a product rule. It is a chain rule, but not a product because there's only one variable x. Remember, this is just representing a constant number. And so this would be e to the negative 3x, and then we'll times this first piece by negative 3, so plus 9, k e to the negative 3x. All right, and then plugging in to our equation, we'll have 4 times y x, and then minus y double prime, and this is minus both, so minus the first one and minus the second one, 3x. And we need this to equal 10 e to the negative 3x. All right, so let's go ahead and distribute. We have 4 e to the 2x plus 4k e to the 3x minus 4 e to the 2x minus 9k e to the negative 3x equals 3x. There we go. We do have some simplifying that'll happen, right? 4e to the 2x and minus 4e to the 2x is going to make a 0. And so look what we have left here. We have 4k e to the negative 3x minus 3k e to the negative 3x needs to be 10 e to the negative 3x. They all have that e to the negative 3x. And so what's going to happen is these two terms have to add together to make this term. And so you're looking at your coefficients here. So 4k, a positive 4k, minus 9k has to be equal to the coefficient on this side, 10. And that will tell us what the actual value of k is. So that's an easy equation to solve once you get to here. So I have no doubts that you can finish that. But knowing that that's kind of what they're looking for is those coefficients have to work out. So divide by negative 5 and we get k is negative 2, which is a solution here. So we are good to go. Sorry. All right, your homework is the skill builder. It is only 2 pages long. So it's skill builder topic 7.2. It's just 1 through 8. They're all multiple choice, or they're not multiple choice, sorry. They're like you have to test each one. So without showing you the actual like solutions on this first question on the skill builder, you have to test this one to know if it'll work. And then you have to test this one to know if it'll work. And then test this one and then test the last one. And that's kind of like how you'll go about solving those. All right. All right. Let me know if you have any questions. And then we will do 7.3 and 7.4 tomorrow on Tuesday in class. So whenever you watch this video, possibly tomorrow or Tuesday. All right. Have a good one.